So welcome everybody to our theory gamma seminar. Today we have the pleasure to guest Jan Cieśliński from the University of Białystok, who's going to talk about the applications of Clifford Algebras and speed groups to integrable systems. So Jan, thank you very much for accepting our invitation. It's a pleasure to have you here. The floor is yours.
Yes, so good afternoon to everybody. I'm really pleased to be here and to have an opportunity to share my, my old, in a sense, research, but with some still open and interesting problems. So the title seems to be quite general, applications of Clifford algebras and spin groups to integrable systems. In fact, I focus on Darboux or Darboux background transformations and soliton geometry, integrable geometry. This would be the center of this talk. So it is just some part of probably much wider applications. So a short introduction. Integrable systems, probably well known to you, but just to fix some notation and this kind of things. Linear problem or Lax-pair, zero curvature representation. So we have this system of matrix linear equations. So U are matrices, X are n variables. Of course, pair, Lax-pair, concerned to the case n equal to 2. I'm not sure how call this structure for larger n. They are quite useful in these geometric applications. In integrable systems here, usually the case n equal to is most frequent, most privileged in a sense. By psi, I mean it could be a vector, a column vector, but I mean matrix as a fundamental solution. So non-degenerate matrix which consists of independent vector solutions. The comma means derivative in a standard way, and compatibility conditions for existence of the solutions psi are just permittability of partial derivative, which leads to the standard zero curvature representation. This is a system of equations for matrix coefficients, some nonlinear system. And in the case 2 by 2, we have a lot of examples like the famous AKNS class, KTV, mod KTV, Sine-Gordon, nonlinear Schrödinger, and so on. By the way, if any of you have some questions during a talk, please do not hesitate to ask, just because it is better to answer some questions.
Don't worry, Jan, we will do it.
Okay, so Darboux transformation. This is because in general, existence of a Lax-pair implies, among others, techniques like the inverse scattering method, soliton solutions, algebra geometric solutions, and the Darboux background transformation. And I will focus only on this last technique, Darboux background transformation. So first,
Jan,
I will try to...
Jan, one question. Is there any manner to characterize when a Lax-pair exists?
Well, this is, so do you mean what, the having nonlinear system, what about the Lax-pair?
Yeah, if you, given a partial differential equation, you have a related Lax-pair.
No, so this is another topic. I'm not very good at it. Probably the symmetry taking prolongations and so on and so on. I will give some small hints in this direction on some further slide. But frankly saying, it is not so. But geometry gives some hints in this direction. Okay. So it will be set in in few minutes.
Okay,
So
go on.
the group transformation is a kind of gauge-like. It looks like a gauge transformation, formal. And it transformed the linear problem into something like that. And on the level of this transformation, it looks like a gauge transformation, but it is not, because the transformation is called Darboux only if the form of the linear problem is preserved. It is a very strong condition. So U tilde has to have the same form as U. And what, so that the corresponding nonlinear equations, for instance, remain identical. And what does the form of the linear problem mean? Well, this is a kind of my own formulation of this problem, because other researchers usually are not so precise in this respect. So I would like to find, for any Lax pair, to find some set of conditions, like dependence on lambda. In fact, mostly it is a rational function of lambda. It's a relatively simple case. So we mean pole divisor of poles. So poles and their multiplicities. Reduction group or Rube group. So this is also the next. These two are very important. And this, the rest are some less important, but they should be added to obtain exactly the equation we look after. So linear and multilinear conditions on the Laurent coefficients around the poles, they are invariant. Some of them are invariant of the Darboux transformation. Sometimes some other conditions has to be used. These two last points are specific to my approach. So most of people usually look at these first 2 points and then somehow they derive the Darboux transformation. And if they transform equations into the equation, the problem is finished. The significance of these conditions is that they uniquely determine the integrable system. So instead of looking at the nonlinear or linear system, we look at these conditions only. The Darboux transformation should preserve the set of these conditions, usually after imposing specific constraints on the coefficients of the transformation. So some of these constraints add some constraints on the form of the Darboux matrix. What is very important, that various representations of rational matrix functions of lambda considered modulo a scalar factor depending only on lambda, a crucial role. Why this scalar factor? Because when we multiply d here by a scalar factor, which is constant with respect to the x variables, then it cancels. So if D is a Darboux matrix for some systems, then D multiplied by any scalar factor, but scalar can mean depending on lambda, because lambda is also a now okay, there is a lambda here. So lambda is a constant, but in a sense it is important constant. So for instance, in this system is identity with respect to lambda. So actually it splits into a set of some coefficients, some equations by powers or poles of lambda. And depending on the representation, one has different methods. I like, well, it is not my native method, I would say so. So I learned about it maybe several years, no, yes, several years after my studies, in fact. Polynomial in lambda. Gernot Neugebauer found it, probably, but I'm not sure. Maybe Russian authors also. So eigenvalues, which are important in the construction of the Darboux matrix, are zeros of the determinant of this matrix. Another representation, sum of simple fractions. Eigenvalues are poles of d and d to the power -1. This Alexander Mikhailov is probably a leader. Of course, his teachers, Zakharov and Shabbat as well, I think. But technically, Mikhailov made a lot of progress in this aspect. And the third one is almost not known. Alexander Sachnovich. It is very interesting construction, rarely used. It has something to do with ODEs and this transfer matrix which arise during Laplace transformation. So lambda enters only in one place here. N, F, G, and A are matrices. And eigenvalues are hidden in A somehow. This could be, for instance, linear, diagonal metric, not diagonal matrix with eigenvalues on the diagonal.
Jan, like where it comes this expression? Which is the idea of that? What to do?
Oh, well, from this theory of systems, control systems. So for me, it is also not very well known. These matrices are of huge dimension, in fact, because this inverse matrix is, in fact, its dimension is related to the number of poles. So it is a large dimension if you consider multi-soliton solution, for instance. Well, you are right. For me, it is also a kind of mystery still. But anyway, it is quite efficient. It is a quite efficient method. In one of my papers, probably I'm one of very few persons which can understand all these methods and usual relationships between them. Well, then some next method would be the so-called loop group approach, for instance. So one more method will arise in the context of Clifford algebras, and it will be at the end indicated. But so there are many approaches. For me, it is interesting that they are in fact equivalent, but anyway, they are technically so specific that usually people who work in the context of one method are not very well familiar with other approaches. And also some advantages and disadvantages are in each of these approaches. For instance, the second approach is very suitable to Hermitian or orthogonal reductions. These reductions at this level, polynomial, are very difficult and in fact reduces to disequivalence, and so on, and so on. So the simplest case, the simplest but very important Darboux transformation is one pole transformation. So the D has just one pole in lambda, P does not depend on lambda, and the inverse of D also has one pole in different place. Actually, if we assume that D is linear in lambda, or has one pole, and the inverse of D is also linear or something like that, then practically necessary implication, result is that D reduces to form like that. Or modulo, maybe normalization matrix. And also, this is very, very strong result that this projector P can be expressed by this so-called old wave function, evaluated at these poles. And in more general case, so in fact, in general case, when D is any polynomial in lambda, of course, this D is also polynomial because we can multiply it by lambda minus lambda 1, and then we obtain the linear is lambda. And as I said earlier, multiplication by a scalar factor is allowed, does not change the transformation. So when D is a polynomial in lambda of any order, then we can compute determinant of it and find eigenvalues and such a constants. Of course, and if all eigenvalues are simple, not multiple, then this constant give you a form, has the coefficients of the polynomial D of lambda, up to normalization, so up to some matrix which does not depend on lambda and can multiply all of that. But if these eigenvalues are multiple, then technically it is a little bit more involved, but just technicalities. In physics, we can say if the eigenvalues are multiple, one can split them a little bit to obtain different eigenvalues and then take a limit at the very end of the calculation and everything will work as well. But anyway, yes. And group reductions. For instance, if trace of the matrices of the Lax pair is 0, then the determinant of D is constant, and then very important result that lambda must be constant. This is important, that lambda are not allowed to be to depend on x. This is some involution, some loop algebra. This is the corresponding loop group. A square must be 1 to be consistent with this. Then we have another constraint on lambda and some constraint on this p vector, which was there here, this eigenvector. And so on. This is some Hermitian algebra on group. Of course, some generalized Hermitian. If B is 1 unit matrix, then you have exactly something like a unitary group or correspondingly algebra. Then eigenvalues has to be conjugated, and also these vectors have some are related. And this is another group introduced by Mikhailov in the context of this Toda lattices. And what is important is the conditions for mu are can be very easily checked in examples. So if one has some Lax pairs, then one can very easily check that you satisfy some of these constraints. And then we automatically have some constraints on the Darboux matrix. And we are sure that the Darboux matrix will satisfy these constraints and will give us a solution which satisfies the given reduction. Take a very simple example, the Sine-Gordon equation. This is probably the most known Lax pair for the Sine-Gordon, the standard one. And this is expressed in the sigma matrices. This is a gentle introduction to Clifford algebras, by the way, because later on, usually these matrices will be expressed as a linear combination of some Clifford vectors. And sigma matrices are some simple example of them. The set of constraints preserved by the Darboux transformation is rather extensive. So if you would like to write a list of constraints which these constraints. It would be, well, probably it is not important to write it down. But what is very nice is that if we just assume that both U1 and U2 are linear in lambda and lambda inverse, so if you have this form with A, B, and C are some 2x2 matrices, and we assume this group reductions that this is SU2 the algebra, in fact, that the coefficients, these three coefficients belong to SU2 Lie algebra, and this is some involution, some skew symmetry, I would say so. Is some constant. In this case, above this E, this bold E is in fact sigma 2. So this is enough to obtain the sine-Gordon equation modulo variable change. So for me, it was quite surprising, in fact.
Yeah, one question. How do you know there is any way of knowing how lambda will appear up to the initial partial differential equation? I mean, there is some way to knowing from the sine-Gordon equation that the black sphere will be linear or polynomial lambda or whatever. There is some idea, or?
Yes, there are some methods to derive it. Now, this prolongation method of Walkquist and Estabrook and some works by Wolfgang Schiff, for instance, even and other persons. Probably one can add this somehow, but frankly saying, I never was familiar with that. So my approach is rather, well, let us assume from the beginning the case 2x2, such or other reductions, make compatibility condition, and let us see what is the outcome. And then we can obtain some class of integrable systems. So, unfortunately, I'm not an expert to derive Lax pair for a given equation. I think that this prolongation theory is something which should be.
Okay, never mind. I was just curious.
No, so my approach was always from the other side, other end. So to assume, for instance, these two, assume some group, assume some form with respect to lambda, and see what is the outcome. It is quite a fruitful approach, by the way. So probably, but your question is very good, because in fact, if you would ask me what was the motivation for the second half of my talk, it was exactly as I say now. Some very simple assumption at the beginning, and to see what is the geometry after that. And the answer was quite interesting. That's all. Maybe, okay. Yes. So now how geometry comes into the play? No, by the same formula. Same formula, the Syntafel formula, because this formula is some, maybe 40 years ago, was at some seminar, Antoni Sym, as far as I remember, have this formula for the tangent vectors. And Jacek Tafel noticed, well, these formulas can be integrated.
Indeed, Jan, I have a work to describe all these formulas geometrically with cohomologies, and I did the since formula. I did also the how he's called. I don't know.
So probably you know more than me about the underlying structures. So we can discuss it, or you may. I will be very interesting to. Well, I know I remember, but I never was able to read it too carefully, probably. Yes, now I remember probably which paper you mean. Okay, so but anyway, the prehistory of this was that this was matrices, 2 by 2 matrices, so on. This was these tangent vectors. Lie group, in fact, well, okay. So F is lambda family of submanifolds, and if psi belongs to a Lie group, then F belongs to at least in the matrix case, because maybe in abstract group case, it probably could be some, but isomorphically algebra probably. Probably have you know better than me about that. But anyway, in the matrix case, if G is in SU2, then F belongs to SU2 Lie algebra. So Anthony Sim obtained first these formulas and then the corresponding geometry, for instance, for the second equation. But Jacek Tafel noticed, well, this formula at some seminary, in fact, can be integrated. And then this Sim or Sim Tafel, now sometimes Sim Bobienko, because Bobienko also obtained this formula in the context of CMC surfaces independently, probably, but later.
Sorry to interrupt you.
No.
Yeah, I just had to take a look at my own paper because I remember because I integrated the Sintafel formula with cohomology. I did also the same with one of your formulas. Indeed, my paper is the Cieśliński D'Oliva formula in the Gelfand. So it was fun.
Okay, thank you. In fact, but anyway, well, this formula was so much. For me, it would be rather the same formula. He was, in fact, seen this formula behind all this because he's in this F. The integration is, in fact, well, for him, F was crucial. F was the submanifold he was looking after. But anyway, this formula for this tangent vector, for the second derivative, were very important because then we can have the so-called fundamental forms, including the metric tensor of this submanifold. And these other fundamental forms, the second or the third, so these forms which are crucial for this differential geometry of submanifolds can be obtained without knowing the explicit form of psi. So they are just on the level of the Lax pair, of these matrices of the Lax pair. It is very interesting, very strong in a sense. So to any Lax pair, in fact, corresponds some geometry of submanifolds, because this formula can be applied actually to anything, in fact. But somehow it leads to interesting geometry, because if you have any object, actually the psi itself is also in a Lie group. U is in a Lie algebra, so one can say, well, maybe this is also interesting object. They are not so interesting as this object. So if G is SU2, then F is a lambda family of surfaces or immersion in L3. And usually these are interesting immersion. The inverse path from geometry to integrable system is not so straightforward, but to some extent it can answer Javi to your question that, well, geometry is a source of many non-parametric Lax pairs. So some linear Gauss-Weigert equations, which gives you a kinematics of tangent and normal vectors of this frame associated with a surface. The kinematics of it gives you a kind of non-parametric. It looks like a Lax pair, or like this a set of linear equations, but without a parameter. So in a way, return to the very beginning. And from geometry, always we obtain something like that. So psi is a moving moving frame or basis of tangent and normal vectors. So it is some element of some orthogonal, say, group or something like that. And this is its evolution, which gives you, which is given or prescribed by some matrices from some Lie algebra. And this, the Gauss-Weingarten equations can be encoded like something in this form, but without a parameter. But such parameter can be introduced by Lie point symmetries. So if we search for symmetries, which are symmetries of the nonlinear system, but are not symmetries of this linear system, then this parameter of symmetries is visible in the linear system and can be interpreted as a spectral parameter. Usually it works. And the second, this was especially Michał Marwan. His contribution to this was probably maybe Cieśliński also. They found a lot of examples, new examples of some interesting geometries which have no lax pairs, but after this technique, some integrable system appeared. New integrable system appeared. And then immersion in sphere and quadrics. So we can sometimes relate, have a lax pair in a larger space, and then the spectral parameter is related to the radius of this sphere. This was an idea of Adam Doliva, in fact, but I also made some examples in cooperation with Yuri Aminov. Many open problems, because in fact, in this direction, almost nobody made a lot of, I think that this is quite open field. And this is an example. Actually, this slide is related to this case. I searched where it is. So how to, so this is formulated in some theorems. So Antonism, if we have psi, this is a fundamental solution to the standard sine-Gordon lax pair. To this lax pair, which is very well known on this one. And then let us compute the sim formula. And what is the outcome? That of course, it is interpreted that the result is in the Lie group, in the Lie algebra. So it is spanned in the space spanned by the generators of the Lie SU2 algebra. So the x, y, z can be interpreted as some coordinates of some, of course, x, y, z depend on these independent variables, which are parameters on some surface, R3 surface. And this surface has a constant curvature, dependent on lambda, by the way. And moreover, x and y are asymptotic coordinates on this surface. Physicists usually call them light cone coordinates. And some fact which was very intriguing for me, that if psi is still in SU2, but we make almost no assumption on the lax pair. Any matrix which is, of course, linear and in lambda 1 over lambda, and constant matrix can be also. So it is some inhomogeneous linearity, let us say so. Demand these two involutions, which of course make smaller the number of the variables. But anyway, the Gaussian curvature of this surface is exactly the same. but the coordinates are wild, are any. And also some Saint Gordon can be also deformed by some changes of coordinates and so. So perhaps you have some gauges, changes of coordinates, and so on and so on. But anyway, geometrically, it is still just the pseudospherical surfaces. For me, I very like this result, but it is a very funny thing. I consider it one of my most interesting results, in a sense, in my life. But anyway, this is quite just an observation, but I like this observation. I don't remember if anybody cited this paper. Maybe no.
I learned these things from Grunlar, from Michał.
Yes, yes.
And afterwards we prove we check other examples with other Lie groups, and it was really nice. I mean, you pick up F for these cases, and you start getting certain surfaces, yes, and with nice Gaussian curvatures and other geometric properties. They are cool indeed. I can compute it. I understand it more or less, but I'm still quite shocked that something like that happens. I have the feeling that I don't understand fully what is going on. But it's cool.
Okay. Yes, probably I should also take a closer look on. Yeah, I seen these papers by. Well, okay. Probably we should. Yes. Okay. This is very nice. Very nice remark. Important remark, of course. Okay. And now we. Yeah, okay, but now we have on the path to the main goal of this talk. So Clifford Algebra, probably most of you know very well about them. So this is the most straightforward formulation. We have some space, vector space, maybe pseudo-Euclidean. This anti-commutation relations, which so some free algebra, but with this relation also, which leads to the Clifford algebra, which consists of scalars, vectors, bivectors, multivectors, pseudoscalar. So this very nice Clifford product simplifies any products of vectors to this finite dimensional, but to n-dimensional space. Well-known examples n equal to 3 and this signature, so Euclidean case, Pauli matrices, but of course, this is a little bit tricky, because what about sigma 1 multiplied by sigma 2 by vector? Now, if it is the real case, so we can, we in a sense assume that we do not know that it is I sigma 3, for instance. This relation is not needed at this level. So we have bivectors, and E1, E2, E3 is so it is maybe not exactly. Pauli matrices has some additional constraint which simplifies these structures to three-dimensional space. But no, never mind. And the Dirac matrices. Now I realize that Pauli matrix and Dirac matrices, maybe it is not perfect name, because this multiplication, this constraint imposed on this pseudoscalar, in fact, makes this structure even simpler in a sense. But okay, so it is another look at the Clifford algebra. So this is Clifford product, that anti-commutator of any two vectors is proportional to the unit of the Clifford algebra. This is a scalar product. So in fact, parallel vectors commute. It follows from this formula. And orthogonal vectors anti-commute. So this is more or less equivalent to the formulation in the basis, which was given on the former slide. And here already some geometry comes into play, because inversion with respect to the circle can be expressed. So if you have a product, then of course the inverse vector can be, then it is of course this. If you in this product put V equal to W, then this formula is immediate. 2 cancels and so on. And this is a formula for the inversion with respect to the unit. Yes, in this case to the unit circle. Also, reflection with respect to the hyperplane orthogonal to n is given by this formula. So the multiplication of 3 vectors. So n defines our hyperplane, V is a vector, and V prime is a reflection of V with respect to the height. Very nice formula. Of course, by some very simple, very elementary computation related to this, one can obtain this formula, which is closely related to geometric pictures, that you can see that the reflection is this vector minus the double normal component of this vector. And immediately we have the Cartan-Dieudonne theorem that any isometry, well, maybe not the theorem is, well, the theorem is that any isometry of V can be represented as a composition of that most n reflections. This is the theorem. But from this theorem and this formula, we can express any isometry. So this phi prime is an image of the V in some isometry, which is expressed as a composition of n reflections. So this is this composition. So first reflections with respect to n1 is given by this, and then the result is reflected by n2, and so on. -1 is related to this minus, which is at each step performed or applied. So this formula. And now we can see that any isometry is related to some product of, in fact, unit vectors, or let us say unit vectors. And it underlines, or it is maybe one of motivation for introducing the pin and spin groups. So if K is even, because even number of reflections give us the isometries which preserve the orientation of the. So if K is even, then so this product by definition belong to the spin group. So spin group is a group is the multiplicative group which is generated by unit vectors belonging to the Clifford algebra. And so if K is even, so even number, then it is spin. If K is any, maybe not even, then pin group. But here spin would be a little bit more important, so let us keep to spin case, to the spin case. So proper isometry, orientation preserving, is given by this simple formula. The algebra of the spin group is spanned by bivectors, non-trivial commutators one can obtain still. So this is just a computation which shows that it is the algebra and the commutator is closed within the algebra. This is an example. The algebra SU2 is spanned by this. So we have all commutators, but well, at the level, so in a sense, spin 3 is isomorphic to SU2 Lib group. And now we have the following picture. So in the SU2 case, which corresponds to many integrable system, it is very well known and very familiar to any people, to any researcher working in the soliton theory. We have this Lax pair and so on, and then psi depends on belongs to the SU2 group. What are possible generalizations? First of all, we can take more matrices, what was at the very beginning stated. And what was the contribution of Anthony Sim? He immediately noticed that SU2 is an example of a semi-simple Lie group. So he generalized this approach for any semi-simple Lie group. For me, another path was intriguing. SU2 is a spin 3. So what about going in the direction of spin PQ? Of course, one can also think about discretization, including time scales. But discretization, to some extent it was done, but for me it is very intriguing. Even in the Sine-Gordon case, the situation of asymptotic coordinates is clear and very well known, since Bobienko and Adam d'Oliva at least. In the case of laboratory or curvature coordinates, is difficult. It is very surprising. So discretization, in any case, even in the Sine-Gordon case, has still some mysteries, is to some extent open. On the level of Darboux transformation, it is simple, but anyway, there is a lot of open problems here. Maybe I would say that it is open problem in general, in a sense. There are some very few results, I would say so. And we will focus on the very simple case that U mu, so this U and V, U mu, because mu can be M, are spin PQ valued, and U mu, all U mu, 1, 2, and any, are simply linear in lambda. And yeah. I touched the problems that can be lambda and 1 over lambda, nothing more.
Jan,
yes.
One curiosity, what I did with Michał was partially to solve this problem. I mean that you could generalize all these immersion formulas and formalisms when the independent variables are of any order, yeah, and when you change the values of the U mu, so maybe
sorry, I got lost. So what do you mean? Which?
I mean that I generalize the immersion formulas in all this stuff
yes.
for the case when the independent variables x, y, there are more of them, not only two.
Yes.
There are more, and you could do it. And also I investigated the case when the U mu are evaluated in a general Lie algebra. So the thing that they are spin evaluated, it should not be a problem for that.
Yes. Well, actually, yes, you are in a sense right, because you mean that spin groups have some metric representation, for instance. Yes, because one can look at that also in this way, that, well, spin groups, similarly as spin 3 has representation by 2 by 2 matrices and so on, any spin group can be represented by matrices. Yes, in a sense, this is right, that one can say that, but you will see some thinking in terms of spin groups simplify the problems a lot. This is my idea, that this is not, one can even by brute force to follow, and to try to work in some matrix representation. But it is technically difficult and somehow not elegant, I would say. What about working in the Lie group and spin as a special case of a Lie group? I don't know, maybe it is also not. So we will see the next, and we can maybe in future compare on to say, yeah, okay. So, so I will just, maybe I should go straight forward to the conclusions, yes. So I will just present some class of problems, surprisingly rich, in fact, which is associated with this case. That U is first in spin group, so it would be spanned by bivectors. So we assume this kind of problems. And U can depend on X, so X as a vector, X1 and X2 and so on, and lambda. So this kind of problems. And moreover, usually dependence of lambda would be rather simple. Lambda may be 1 over lambda and nothing more. Of course, yeah, so psi is spin valued, the solution. Motivation came from isothermic surfaces, where Anthony Sim in papers of Darboux found some rather complicated looking system of 10 equations for some 5 functions which satisfied. So it looks like, well, now it is obvious because this case of Darboux was conformally invariant, so this group was more or less evident. But anyway, we found rather easily, maybe I found it, I don't remember exactly, this SO2, SO41 representation, then trying to simplify like SO3 matrices has representation in SU2, so 1 dimension less. Any spectral problem in SO3 usually is written in SU2 and then it went. So I translated it into SP11 4x4 matrices. But anyway, it was, and then I noticed that, but I noticed it on the level of matrices. This matrix is 4x4 can be expressed by some generators, and it simplified computation. So we wrote this paper, which in fact triggered a lot of developments by top class geometers. So it was very, I think, stimulating result in differential geometry. But they all came in some direction. My direction was a little bit different. So this approach, which I will present now, well, this is just isothermic surfaces, this original formulation by Darboux and so on. So we have 2 fundamental forms, Gauss-Codazzi equations. So this is a system. And what is important is that the isothermicity of a surface is an invariant under conformal transformation of L3. So if we have a surface and then make a conformal transformation of the whole space together with the surface, then the resulting surface will be also isothermic. If the input was isothermic, then the output is isothermic as well. So this approach, probably nobody still pursues this approach, but for me it is interesting. This kind of interpretation, this kind of obtaining some interesting geometries. So, given 2 vector spaces with some quadratic forms, so we have some scalar products here and there, some, for instance, of course, some signature and so on. These are given things. And then we postulate this spectral problem with these matrices. So this problem is defined by a Clifford vector, in fact. So this vector, this is a vector. So the U has product of a constant vector, of a basis vector, in fact. And, oh, sorry. O, czekaj, teraz nie mogę rozmawiać już. Czy mamy teraz... I'm sorry. I so rarely use my cell phone that I forgot to
Never mind. It's
okay. So actually, my brother called, which I very rarely contact with him. So I'm sorry. But anyway, we have. So this is this basis vector, by the way, belonging to this first space, and a mu is some variable, actually vector, so depending on mu from the seconds. This is a kind of auxiliary space, in fact, and b mu is some vector from this first space. So we have some number of functions which are components of this Lax pair. And as a result, we have that psi belongs to this spin group based on this simple sum of these two spaces. This is more explicit, why this var? This is some artifact. Probably wow. Actually, okay, this var is just a bug. Shouldn't be here.
yeah, sure.
Okay. Just before the seminar, I produced a file without this, but anyway, I took it.
That doesn't matter.
Okay.
Don't worry.
Okay. So this is these equations, by the way, were obtained in some cases by were considered by Ablowitz and Beals, for instance, but in the matrix representation. So these papers by these people are very difficult for me, for instance, to read because some metrics of special forms, some compatibility conditions, they look for me rather involved. Okay, and then there is some lemma that this A, or this A, by virtue of compatibility condition, forms some orthogonal basis in this auxiliary space. But anyway, a theorem is, because probably I'm sorry. Okay, because this is maybe the simplest example. Maybe first of all I should. Maybe this is a general theorem, but it was motivated by the example, which will be on the next slide. So here we have the same formula, and it is a little bit discouraging that it is in quite many dimensional spaces. So the dimension of it is Q times R. And the Gauss-Ricci Codazzi equations coincide with the generalized wave equation, whatever it means. So this is an example of in this. This is the motivating example. So if we have this case that V is R3 and W is R11. So Minkowski two-dimensional space, then we have some two-dimensional flat. So the Gaussian curvature is 0. Yes, immersed in a six-dimensional Minkowski space. Okay, it is the the compatibility conditions are still these equations. Isothermic. But anyway, the surface is not isothermic. So at first it was a little bit discouraging. Well, the same formula yields not what we would like, what we wanted to obtain. But it was even better because a projection of this two-dimensional structure, immersion in 6 dimensions, when we projected it on appropriate subspaces, some null subspaces. So each of these 3 vectors is has 0 vector, so its square is 0. Maybe Lagrangian subspaces, probably it could be called like that. So then the coefficient by this basis vector, this new base, gives us 2 isothermic surfaces, which one can recognize in them dual surfaces or Christoffel transforms. And so the general idea is to project this object given by the same formula. Oh, by the way, evaluated at 0. At 0 is, well, at other lambdas, it's not clear what is the outcome. Not so much clear. So then, but it is sufficient. So it is, so in the sign Gordon, we have a lambda family of immersions. Here we have a single immersion, but it is not bad. The same formula and all this apparatus works quite well. Also, if only at 1 lambda we obtain some interesting geometry. Darboux transformations and everything works equally well. So the idea is to make some projection. And in fact, this is probably the simplest way. We project this second space in this outer product on the R is, for instance, in this way, when these are some constant. And then we obtain a map into V. So if we apply this projection, then we have some submanifolds immersed in V. And we suppose that it will be some interesting geometry. So we have, as ingredient, we have this assumption. So these spaces, these dimensions, and so on. Then some, okay. So we automatically obtain, without any further assumption, except compatibility conditions. Of course, this structure is important, and then compatibility conditions make some another constraints, of course, and this projection. And then we have some geometry of submanifolds. And this is interpretation. The fundamental forms for this geometry is like that. So this beta is, here we have, so if we expand this B, so its coefficients are given by these betas. So these betas are encoded, are functions encoded at by these Clifford vectors. And H is also, H is something like that. So by these A vectors and by this projection. So we have these fundamental forms. The normal vectors make flat normal band, which is also interesting. These are submanifolds for any choice of these constants are submanifolds with flat normal bundles. And Gauss-Codazzi coincide with the so-called generalized wave equation, and so on and so on. Special cases that we have, and this space n and this auxiliary space and is two-dimensional Minkowski isothermic surfaces in Rn, equal dimensions, Euclidean both. Then we have orthogonal, that's Rn, with this constraint on the Lamé coefficients. These H are coefficients of the metric, of the orthogonal matrix. Lamé coefficients usually called. Then we have this class was that the sum must be constant was considered by Bianchi, of course in different mathematical setting, but anyway. And when we have three-dimensional space and W is three-dimensional Minkowski, then we have the so-called Guichard nets. Yes?
Jan, sorry, but we should think about finishing.
Yes, of course. So this is almost the end. Well, and then this, yes, I'm sorry to, which time it is?
It's 20 past.
25. So give me 5 minutes maybe just to see.
Yeah, sure.
Okay, then now, yes, so for Darboux transformation, the crucial point was the zero of the determinant, yes? Because now I can show some analogies that we have. So now I can refer to these slides. The Darboux matrix can be polynomial and so on. And we have some group reductions. Everything would be translated into the Clifford setting. Yeah. So the traceless means determinant. Well, the traceless, it means that there is no constant term in this matrix. This is very interesting. Determinant corresponds to the Clifford, to the spinor norm. So it is Darboux matrix Clifford is spin group. So beta is one of these. So this is this Clifford. Alpha is the so-called main automorphism, reversion, and conjugation. So So these are some standard operation of the Clifford algebras. Very simple, in fact. So here we just the Clifford vectors are changed for lines. This is a reversion. So we reverse the order of all Clifford components and so on. Very, very simple operation to be checked. In all, even easier in this matrix reduction. Certainly easier. So this corresponds to the to this. Yes. So okay. Probably one slide is a little bit missing, but anyway, the Darboux transformation can be one soliton, so instance, so can be expressed by some Clifford vectors, which are in fact some rotation, some Clifford rotation of psi, which is this spin element, known spin group element, and we rotate some constant vector, which has this structure related to the spaces V and W and V. What is intriguing is that these vectors are contained in the Darboux papers, for instance. The transformations for the sin soliton submanifolds are very simple. This is the old element in the spin algebra, so by vectors, and here you have vector, and here you have vector, so it is also by vector, so very simple transformation. And what is this P and V? These are these vectors, just head denotes normalization, so these are unit vectors. So it works perfectly, and in very simple case, almost as in the pseudospherical and sine-Gordon case. But what is very challenging to obtain this formula for multi-solitons? My guess is that we search zeros, but this is just guess, zeros of the spinor norm, and then at each zeros we have these vectors, and then the challenging for me, maybe it is known for the specialists in Clifford, how to construct the element of the d of lambda, knowing these Clifford vectors which are zeros. So in fact we have, well, and in fact it is not exactly the spin group, because the spin group can have zeros. So and these zeros matters most. So I'm sorry for prolongating my talk. These are some open problems. And thank you for attention.
Thank you, Ian. I'm sorry, but maybe we have no time to finish it, to make questions. So please send me your slides. It would be nice to take a look, and we can talk when you will be in welcome. Okay?
Yeah, I think that maybe because I'm not quite sure how much you all are familiar with this Clifford. So if for anybody, for some, if there are people which are interested in this last part, which is most crucial, in fact, so perhaps someday I can give a talk without this introduction, without this matrix introduction, and it could be shorter and more focused on the main content of my.
It could be nice maybe one day to do so somehow, But
so once more, I thanks, and I apologize one more for prolonging.
No, there is no reason to apologize. It happens. Only have a complicated day. It's been a pleasure to have you, Jan. Really, thank you very much for giving the talk. And send me please your slides, and we'll talk forward about it in a while. Okay?
Okay.
Thank you. Really.
Thank you very much.
We are finished today. Thank you everyone for assisting, and see you in a week with a simplified approach to the free-body problem with Moreno, with how is it? Come on, I don't remember his name now. Okay, please check on the web.
Giovanni Moreno?
Yeah, Giovanni, yeah, it's another guy that was in the Institute for Advanced Studies, and I don't remember now. Okay, see you. Thank you, Jan.
Thank you very much.